So in the previous video, I led you down this discussion of basically chemical shifts relating to particular hydrogens within a molecule or protons within a molecule. And we talked a little bit about electronegativity. And we said, listen, electronegativity is an electronegative atom that's very electron greedy, and it's going to suck all of the electrons around it. And what it has left over are these protons, and these charges get exposed to a magnetic field. And the more electronegative the atom is, well, the more exposure that these protons are going to have. And if those protons are more exposed, then they probably are going to affect the magnetic field a little bit differently than if they're not getting electrons sucked by another atom within the molecule. And then we talked a little bit about this idea of methyl groups. And we said the lower the number of hydrogens that a carbon has, the more downfield that signal is going to be. All right, and this is a little confusing, and I mentioned that in the previous video as well. It's kind of taken us back a little bit because we don't really necessarily assume that is going to happen. So for instance, let's say that we've got these molecule or these atoms on a molecule. We've got two CH3 groups on the end, and we have a CH2 group in the middle. So if we take a look at this system, these order or arrangement of atoms within this molecule, what we have basically said in the previous video is that the CH2, which is here in the middle, that is more covered up by the CH3 to the left and the CH3 to the right, this will have more of a downfield signal or shift in the NMR. And a lot of people, when they first learn NMR, are very confused. They don't really understand why this is happening. So we need to put an explanation on it. We need to figure out, well, why is this going on? Why is this somewhat unexpected? Because it looks like if the left-hand side and the right-hand side, it's surrounding the middle carbon and the middle hydrogens. If they're surrounding it, doesn't that mean that it's more shielded? And if it's more shielded, doesn't that mean that it's not as affected toward the magnetic field anymore? And wouldn't that be upfield and not downfield? All right, so that is the problem every time people learn NMR. And the reason is because we're not looking at bulkiness. We're not necessarily looking about how large groups are on either side of those protons or the carbon that the protons are attached to. That's not really what any of this is about. All of this is about is magnetic field, and magnetic field is all about the positive and the negative charges. I don't really care how bulky something is. I don't care how large something is at this moment. I need to make sure that we put a focus on the charged species within a molecule. So what do I mean by that? Well, let's take a look at this molecule in a different perspective. I do not want you to think of bulkiness on either side. I don't want you to think about how large those groups are because, again, that is where the problem happens with most people. You need to think about charge, positive, negative, electronegativity. I mean, that was rule number one, wasn't it? It was all about electronegativity. So it's all about electronegativity here. So if I had to compare the difference between the carbon and the hydrogen, what I will find out is that the carbon is more electronegative than the hydrogen is. Okay? So because of that, there is an electron pull that's happening here between the carbon and the hydrogen on that carbon. Now, it's very slight, but it's there. And when I say very slight, compared to other groups that might be present, like halogens, right? So if we're just comparing carbon and hydrogen, we have to put a basis, a theory against why CH3s are upfield, CH2s are more downfield, and CHs are even more downfield than that. And here's the reasoning about why this is going on. So if we take electronegativity into an account, this carbon is fighting and pulling between two hydrogens, right? Okay, well, let's compare that to another type of molecule, and let's look at a CH3 group instead. And then we'll need another type of molecule that's similar, but it's a little bit different at least. And it will just be one carbon that we're going to be focused on, not three. Okay, so here's the three examples. And they're not related to each other. I mean, the first one and two are, but the third one's not. And that's not really the point of this example. The point of this example is to put some explanation behind what we're getting ready to find out. So this particular carbon is electronegative. They all are. They all have electronegativity values associated with them. They might not be the most electronegative atom on the table, but that doesn't quite matter here. We're comparing the electronegativity between the carbon and the hydrogen. So in this first example and the second example and the third example, we're going to be focused on that particular carbon and what it actually has to fight against, all right? So here I've actually labeled the wrong one. I don't want to focus on that one. I want to focus on this one, all right? Okay, so let's look at number 3 first. I think this will be easier to explain, and then we'll build on top of it after that. So with example number 3, here we have a carbon, and that carbon has another carbon, and another carbon on it. They all have equal electronegativity values, right? I mean, pretty much they're all almost identical, except for that carbon has a hydrogen on it. So this carbon, like many electronegatives, it's going to suck electrons away from that hydrogen. And when it does that, well, that carbon is a big old bully. And that carbon is going to bully that hydrogen from its electrons, and this becomes more positive. Well, this is the way that NMR works, right? We're applying a magnetic field onto the protons. So what this basically means is that that charged hydrogen is charged. It's charged with positive, and that's what we want. But in this particular example, carbon has only set its sight on that one hydrogen, and that is it. And because it's more electronegative, that carbon is the bully, and it will bully that hydrogen out of a little bit of lunch money. And that hydrogen really can't take up for itself, right? It's just that one hydrogen, that one carbon, and that is it. All right, so now let's take a look at example number 2. With example number 2, this carbon is still electronegative. It's more electronegative than that particular hydrogen is. But the problem here is that there's hydrogens on both sides. We've got a hydrogen here and we have a hydrogen there. Basically, what that means is that hydrogens brought the buddy to the lunchtime. And those two hydrogens take up for each other. So this carbon begins to pull away from one of those hydrogens, but the other hydrogen is there to counteract it. It doesn't let carbon get away with the bulliness that it's gotten away with example number 3. So because of that, we do have an electron pull, and that electron pull is behaving a little bit differently here, all right? And then finally, with example number 1, what we see is this carbon on the end, and this carbon has 3 hydrogens all the way around it. And those 3 hydrogens, well, we've brought 3 friends to lunchtime, right? So if that carbon comes into the picture and says, I want your lunch money, then that hydrogen's basically going to say, well, no, I've brought 2 buddies with me, and you're not getting it today, carbon. So there's still an electron pull. There's still the electronegativity that's associated there, but this carbon is fighting against these 3 hydrogens at one time, where in example 2, that carbon is fighting against 2 hydrogens at one time, and in example 3, that carbon is fighting against 1 hydrogen at a time, and that is it. It's more manageable. So because it can have its way in example number 3, this hydrogen is way more positive versus example number 2. Yeah, these are positive, but not as positive as what we would find in that very first example with number 3 that we did. And then finally with example number 1, we saw that there's 3 hydrogens to fight against, and this is positive, but it's very faint. And the reason it's very faint is because carbon now has a kind of triplet that it's going to have to figure out how to fight against. So this is what gives rise to the different signals in NMR. It's still electronegativity based, but it's not bulkiness based. It's not how covered up the protons are. It's about the actual charges that are on the actual protons. All right. So what this means is that in NMR, we're going to have a spectrum that begins to look like this. And what we will find are CH3s that are more downfield or upfield. And the reason that they're more upfield and closer to the zero mark is because they're not as positive. And if they're not as positive, that magnetic field basically can latch on to them a little bit earlier on, and then it doesn't take as much energy to get them to flip and then all the way back down. So those CH3s are going to be affected first, and then the CH2 groups are going to be affected next. And that's because these, well, the first round, there were 3 hydrogens that I had to fight against. This one is slightly more positive because carbon only has 2 to fight against. And because it's slightly more positive, it takes a slightly stronger magnetic field in a way to get these things to flip and do what they need to do. And then finally, we have the CH group instead of the CH2 group. And that's because carbon only has to fight against 1 hydrogen and not multiple ones. So this particular hydrogen is the most positive, and that magnetic field will grab on to that hydrogen, and it will take a little bit more energy to get that thing to flip upside down and scream the signal out in the end. And this is why CH3s are more upfield than CH2s, and that's why they are more upfield than CH groups. Now, I want you to keep in mind, we are only comparing CHs to each other here. Okay, that is it. So there's tons more functional groups that can go into a molecule. And those functional groups will carry with them maybe electron polar groups like we saw in the benzene and substituted benzene reactions and so forth. But what we're really comparing here is the difference between the carbons and hydrogens. There's a slight difference, and that slight difference is due to electronegativity, just like all the other ones are due to, but it's all about how the carbon is pulling away from the hydrogen. All right, so now that we've got this kind of in place, I want to talk more about being able to figure out which carbon or protons would be the most shielded and which protons would be the least shielded. So here I get this compound. It's CH3, CH2, CH2Cl. And I want to go ahead and name this thing just to do a little bit of review in the alkane world. And it looks like chloro is right there. So if I'm going to name this system, that would be carbon 1 and carbon 2 and carbon 3. So this looks like it's a 1 chloro because chloro's on the first carbon, and there's 3 carbons in total. So this is a prop, and it is an ane because it's all single bond. So 1 chloropropane is what we have in this example problem. So the example is going to say, please circle the ones that are the most shielded, and please circle the ones that are the least shielded. All right, so it's all about shielding, which is all about how the magnetic field is going to latch on to these things, and electronegativity is going to play the part here. So this chlorine is electronegative. It's the most electronegative out of the molecule, right? So this is where we're going to start, and that electronegative atom will do what all electronegative atoms do, and it is a sucking the electrons up, right? So basically what this means is that this carbon with the 2 hydrogens that are nearest the chlorine here, this one will have the least amount of electron cloud around it because all of the electrons are getting sucked by the chlorine on the end. So because of that, this particular carbon at carbon spot number 1, this is the least shielded out of all of the protons that are in that molecule. And it's due to the electronegative chlorine that is present. The electronegative atom is sucking electrons, and that sucking noise is pulling those electrons away, so this is the least shielded out of the bunch. So when we talk about shielding, we are talking about the electron density almost every single time with this, right? Remember, shielding is all about positives and negatives. That is how NMR works. It's by a series of magnets. All right, so this middle carbon with those two hydrogens, it's further away from that chlorine, so that chlorine can't suck those electrons as much. And then finally, this carbon on the left-hand side, this has 3 hydrogens, and it's further away from chlorine, so chlorine doesn't have an effect like it does on the middle, which it doesn't have like it does on the first carbon that's nearest. So what this means is that carbon number 3, this is the most shielded. So think of the shielding in terms of electrons. The first carbon is the least shielded, meaning it has the least amount of electrons around it, and then the third carbon is the most shielded, which means it has the most electrons around it. And all of that is due to the chlorine electronegative atom. All right, so that's how we would answer one of those types of example problems. So let's do another, and this time let's do something like CH3, and then CH2, and then carbon, double bond O, and then let's do another oxygen there maybe, and a CH3 group. All right, so if you go back and take a look at the carbonyl family, because this is a carbonyl, which carbonyl is this? Is it a type 1 or is it a type 2? I hope that you would tell me, well, it's a type 1. And the reason that it's a type 1 is because this is a ester group. And remember, there's just 2 really major functional groups in type 2. So 2 functional groups in type 2, and that's an aldehyde and that's a ketone. So this is a ester group. So how do we name the esters? Well, we name the piece that's on the O first, and that's going to be methyl. And then we name the longest carbon chain, which is a prop, and then we add on the term O8 at the end. So this looks like it's going to be something called like methyl propanoate. So the same question is going to happen. Which one is the most shielded and which one is the least shielded? All right, so let's compare where these electronegative atoms are and where the protons are in regard to that. So if I take a look at this example problem, the O's are the electron suckers, right? These are the most electronegative out of the molecule, and those oxygens have always been electronegative. This is nothing new to us. It's old news, old hash, move on, right? So if you look at these oxygens, what are they the nearest to? Well, it's the nearest to that CH2 group, and they're near this CH3 group. This CH3 group is the furthest away from all that mess, right? The oxygens are the bullies. This is where all the trouble is happening at the lunchroom. I don't want to be anywhere near it. So if I look at this CH3 group, this CH3 group in particular is the furthest away from the bullies. So this one is going to be the most shielded out of the bunch. It has the most amount of electrons around it because the oxygens are not pulling them away as much as they are to the neighboring atoms that they're beside of. So now the issue is the left-hand carbon or the right-hand carbon. Which one of these is going to be the least shielded out of the 2? So if I look at this particular carbon with the double bond O, that is next door to a CH2, and that oxygen will pull those electrons away. That is going to happen. There's no ifs, ands, or buts about it. And then if I look on the right-hand side, this particular CH3 group, well, not only does that C double bond O pulls it away, but there's another electronegative atom that's right beside of it as well that the other one did not experience. So this poor little CH3 group on this particular end is getting double bullied, right? And we don't want that to happen, so I feel sorry for it. But that's just the way life has treated it so far. So this oxygen is pulling away electrons from that CH3 group, and that oxygen is helping the first bully to pull even more electrons away from it, maybe a little bit better. And because of that, this particular carbon or these particular hydrogens are going to be the least shielded of the bunch. So I really do want these arrows to point toward the hydrogens because that is what HNMR really is focused on, and that's what we are referring to. It's HNMR, not carbon NMR, but HNMR. All right. So look at the number of electronegative groups, and of course the hydrogens that are nearest the most amount of electronegative atoms will be the culprit, and they will be the one that gets bullied. So that's just how it's going to happen, folks. There's nobody in there to stop it unless you want to start being part of that mess too. All right, so now let's look at example number 3. Example number 3, let's say we have a CH3 group, and then here a CH with a bromine, and then another CH, and let's put another bromine there, and another CH3 group. Or no, here, let's make this a little more complicated. Let's erase this one, and let's change this to another bromine there. All right, so here's the molecule. It looks like I have a 1,1,2 tribromopropane molecule. That is the way that we would name that. Again, it's all about substituents. Where do they gravitate toward? That will be your first carbon. So 1,1,2 tribromopropane. So the same question is going to exist. Which one of these is the most shielded and which one of these is the least shielded out of the bunch? All right, so I look at bromine, and bromine, just like in all of the other examples, I will recognize, ooh, electronegative, electronegative, electronegative. They're all greedy. So there's 3 bullies at the bunch or lunch table now. And if I'm going to go into that lunchroom and I look around at this molecule, I'm going to be the furthest away from those bromines that I can if I don't want to be picked on. So the particular carbon that's the furthest away will have the hydrogens that are going to be the most shielded out of the bunch. So the one that's furthest away from all of that mess and that drama that's happening here on the right-hand side is this particular carbon. So that means that this carbon with those hydrogens will be the most shielded out of the molecule. Now I need to figure out, well, which one of these is going to be picked on the most, because the one that will be picked on the most is the bullied the most is going to be the one that is going to be the least shielded out of the bunch. So I take a look at this carbon, and this carbon has 1 bromo attached to it, or 1 bromine attached to it. And then this particular ending carbon on the right-hand side, it has 2 bromines that are attached to it. So you know what I'm going to say. I hope you know what I'm going to say. And the statement here is that these 2 bromines are going to work together as twin bullies. And these twin bullies are going to go in and say, hydrogen, give me your lunch money. And then that hydrogen's going to go, okay, I don't have any buddies, so you're going to have to take my lunch money, and you're going to have to keep it, and I'm not going to have nobody to actually take up for me. Boo hoo 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 hoo. And away it goes. So this particular hydrogen is going to be the least shielded out of the bunch, and that's because bromines will take the electron cloud away from it. Whereas this CH3 group to the left, it's not getting affected by those electronegative atoms over here on the right-hand side. And because of that, the electron cloud around that CH3 group is going to be more dense. And because of that, it is more shielded versus something like that very first carbon that is the least shielded out of the bunch. Okay? So that is how we begin to determine which one of these are the most shielded and which one of these are the least shielded in these example problems. All right, so now I'm going to turn our focus to another different type of example problem, and this looks something like this. So in this example problem, it says, in each of the following pairs of compounds, which of the underlying protons or sets of protons has the greater chemical shift? That is the highest frequency signal. So what this basically means is if it has the greatest chemical shift, then here is my 0 mark. That means it is the furthest down field. That is what this question is after. So the greatest chemical shift is the higher frequency signal. So we're looking at things that are way over here to the left in the downfield area of the bunch, which means it's going to take more energy in order to get these things to flip. And that also means that it's probably going to take more energy because of the charges that these molecules bring or these atoms bring to the table. So I'm going to get A, B, and C, and it gives me an underlined hydrogen that they want me to focus on, and I'm going to have to pick either this first one or the second option. Which one would have a greater chemical shift? I do the same thing for B. I either pick the one to the left or the one to the right, and I need to explain why I picked the answer that I did. And then for part C, I do the same thing, either the one to the left or the one to the right, and then provide an explanation on why you picked what you did. So that's where this video is going to stop. I want you to attempt these on your own, right? So before you play the next video, I want you to go through, answer these A, B, and C, pick out the choice that you think is appropriate, and then in the next video, I'll tell you if you're correct or not, right? So again, no one's judging, no one's looking at your paper, no one knows if you picked the right answers or not, but in your head, I want you to go through, take a look at these examples, answer them the way you think they need to be answered, and then play the next video to see if you got them correct or not, and if your reasoning matched the real reasoning of why you should have picked one or the other. All right, so I'll see you in the next video with the answers to problem number 12, A, B, and C.